Hello everyone, and welcome back. Today we're going to continue our journey through statistics and introduce a set of tests known as non-parametric tests. Now, let us first off get an overview of what we mean by non-parametric. So usually tests that require something about our distribution that we're sampling from, for example, that our distribution is associated to a normal distribution, our two populations are homoscedastic to one another, and so on. These are often referred to as parametric tests. But if we do not require anything about the population that we're sampling from when we're conducting a hypothesis test, then this type of hypothesis test is known as a non-parametric test. Let's go through a couple examples of parametric and non-parametric tests that you probably have already worked through or maybe even heard of on the non-parametric side. So the first couple examples probably should be very familiar to you, and that would be the family of t-tests for a mean or two means, right? So these are called parametric tests. And why are they parametric tests? Well, for example, if we are conducting these hypothesis tests with confidence intervals per se, that means we're going to be constructing a confidence interval for the population mean mu, and typically the confidence interval, if we're working with a two-sided alternative, is going to be of the form x bar minus the margin of error and x bar plus the margin of error, where that margin of error is usually established to be the product of the standard error and some critical value. The critical value for a t-test is typically taken to be a t critical value, and the standard error is usually approximated by the sample standard deviation over the square root of our sample size m. Now obviously, if we do know the population standard deviation sigma, then we would be using a z critical value in that particular scenario. Now, why are we using a t critical value for this hypothesis test? Well, we do know that if our variables in our sample, let's call them xj for example, let's assume that each of these are associated to a normal distribution with some unknown mu and some unknown variance sigma squared. Then if each of those xj's are independent and obviously identically distributed since they're coming from the same exact place, then we know that the sample mean is also going to be associated to a normal distribution with the same exact mean mu and the variance sigma squared divided by m. And if we do not know that these x's come from a normal distribution, then the central limit theorem says that the distribution associated to x bar approaches asymptotically to the normal distribution as you make your sample size arbitrarily large. Right? And that's why we are using a normal distribution, i.e. the distribution associated to our point estimate x bar is going to be associated to some shape like this. And if we take the z-score of that x bar, then this distribution is going to be a standard normal if we know sigma, and a t-distribution with n minus 1 degrees of freedom if we don't. Right? So that's why we use a t-distribution, generally speaking, because we're assuming that our sample comes from a normal distribution, or that our sample size is large enough so that we can employ the central limit theorem to approximate the distribution of what that is. But generally speaking, if you're not sampling from a normal distribution, t and also z will always have error, even if your sample size is sufficiently large. Right? So this is where non-parametric tests would come into play, because if you don't know it comes from a normal distribution, maybe you want to be safe and not build all of your models around that assumption, which possibly might not be true. So one confidence interval that you probably already know that is non-parametric is known as the z-test for proportions. So the z-test for proportions, and in particular the Wald z-test for proportions. So this is referred to as a non-parametric test. And you may be thinking, well, why is this a non-parametric test? Because it has the word z in it, which stands for the standard normal distribution, because we're probably going to be using z critical values for all of our analysis. And you have to keep in mind, why are we using z in the first place for proportions? Well, just as a quick review, the confidence interval for the population proportion p is going to be equal to our point estimate p hat minus some margin of error and p hat plus some margin of error. So it's going to be symmetric, generally speaking, at least for the Wald approach, where the margin of error epsilon is equal to a z critical value times the Wald standard error of the estimate for p hat, which is given to be p hat 1 minus p hat all divided by our sample size m, right? Now, why are we using a z critical value here? Well, if we build a test statistic on this particular structure, which is typically going to be equal to our point estimate minus the claim value of our proportion. And keep in mind that this term is just the approximation for the standard error associated to using p hat as an estimate for p. Then we would just be dividing by that standard error, whether we use WAD or one of the other ones that we may have discussed already. Right? So this is our test statistic. Now, just because we call it a z-stat doesn't mean it's associated to a z necessarily. But if we sort of think about what it means for our sample proportion in terms of representation, what we have here is p hat is just going to be equal to the number of successes in our sample divided by our sample size, right? And keep in mind, n is just a number and xs is a random variable. And if each of our observations are independent, then this random variable is going to be associated to a binomial distribution. So if xs is a binomial random variable and we scale that down by n, then p hat is also going to be in some sense a discrete random variable as well. But generally speaking, since x is random, we sort of treat it as a quasi-continuous random variable, where that discrete random variable can take in some sense a lot of values between 0 and 1. So one can say, okay, well, this random variable is associated to a binomial distribution, but we don't have a binomial critical value, or at least it's not commonly taught anyway. So where does this z-crit come into the picture? Well, you may remember, at least if you explored this with us, there is a theorem called the de Moivre-Laplace theorem. So the de Moivre-Laplace theorem that says that as n gets arbitrarily large, then the distribution of a binomial actually approaches the distribution of a normal, where this normal has a mean of n times p, and its variance, sigma squared, has variance np times 1 minus p. Right? So as n gets arbitrarily large, the binomial can be approximated by a normal distribution. And since it's a normal distribution, we can always standardize that. In particular, we can shift it based upon some value and divide by that standard error. And that particular random variable, since that is a binomial and that's going to be approximately a normal random variable, this is then going to be a standard normal random variable, at least approximately, as n gets arbitrarily large. Now, keep in mind, we are using a z-critical value for that reason, and that reason only requires something about our sample, not the population that we're sampling from. And that's what makes the z-test for proportions a non-parametric test. Now that we know the general difference between parametric and non-parametric hypothesis tests, let's just briefly mention a pro and a con of these types of tests. An obvious advantage of non-parametric tests is that they require nothing about our populations, so that's obviously a good thing, which means we don't have to worry about our sample coming from a normal, or our sample could come from a heavily skewed distribution, such as an exponential or a log normal distribution. It literally could come from anywhere, and our non-parametric test will still be providing us accurate, at least from the statistical perspective, results, although they may not give us the correct answer that we want extremely often, which is where the sort of drawback is in terms of non-parametric tests, because the probability of rejecting the null hypothesis when the null hypothesis is actually wrong actually decreases in some sense. That is, we're not able to pick up the fact that the null hypothesis is wrong when it actually is, right? Which is called less statistical power, which is usually represented by pi, which is the complement of a type 2 error, failing to reject the null hypothesis when the null hypothesis is wrong, right? So what exactly does that mean, less statistical power, when it comes to sample size compared to, say, an equivalent or sort of equivalent parametric test? So this means that we will need a larger sample size for a non-parametric test to achieve the same exact conclusions in terms of failing to reject, rejecting the null hypothesis, stuff like that, under the same alpha. for a smaller n in a parametric test, right? So let's assume that we reject the null hypothesis under a parametric test with an alpha value of 5% with a sample size of 50, let's say. If you were to use a parametric test with still an alpha value of 50%, you would need a sample size that is usually substantially larger than that sample size of 50 in order to get the same conclusion with the same exact strength. What I want to do now is briefly mention a couple tests that we've actually already discussed that are indeed parametric tests. For example, the t-test for two means, the ANOVA test, f-test, Bartley test. And when I talk about Bartley test, I'm also talking about Levine and Brown-Forsyth alternatives, for which you probably already know what they are and what they assume. But all these tests are parametric tests. But I want to do is just give the names of the non-parametric alternatives that we will also discuss in the near future, but at least you should be at least aware of their existence, just in case you do not plan to look at those tests in particular in detail. So if you're interested in doing a non-parametric alternative to the t-test for two means, and that also includes, for example, dependent and independent, more emphasis on the independent case, of course. So if you have like a pair difference t-test, there is a different non-parametric alternative for that. But if you have two independent samples, then a good non-parametric alternative is referred to as the Mann-Whitney, sometimes also called the Mann-Whitney-U test, right? So that is the non-parametric alternative for the t-test for two means. Now, if you have more than two means, where G represents the number of groups, and you have like 3 groups, 4 groups, 10 groups, or something like that, then the Mann-Whitney test cannot at least be directly used, and you would have to use what is referred to as a Kruskal-Wallis test, right? So the Mann-Whitney test and the Kruskal-Wallis test. And both of those, at least on the surface, will test the equality of 2 or more means. Similarly, in the variance world, we have the f-test for 2 variances, and the Bartley, Levine, and Brown-Forsyth tests that are used to test more than 2 variance equalities, i.e. homoscedasticity between multiple populations. And actually, there's one test that sort of brings these two together, and this is called the Conover test, sometimes also referred to as the squared ranks test for homoscedasticity between multiple populations. Right, and we'll discuss the Mann-Whitney, Kruskal-Wallis, Conover, and several other non-parametric tests also in the near future. So what I want to do now is actually introduce two non-parametric tests that are actually quickly implemented that actually do not require any new distributions in order to be known. The first non-parametric test that I want to introduce is the chi-squared goodness of fit test. And the reason we call it a chi-squared goodness of fit test is we're not assuming that it comes from a chi-square distribution, but the test statistic that we're building actually follows a chi-square distribution, even though we're not necessarily sampling from chi-squared, normal, exponential, uniform, anything of the sort. So what exactly does a goodness of fit test test? So what we have here is a distribution of values. Let's assume that these blue values right here represent happiness values, right? So if we sort of look at this symbol here, which is Greek letter phi subscript 0 of x, so that's the theoretical or expected distribution value of happiness. So what we have here is it increases from 9 a.m. to 11 a.m. and then it increases to 1 p.m., increases at 3 p.m., but then after 3 p.m. it starts to decrease as you move throughout the evening. So that is our theoretical distribution of happiness throughout the day. Now, that is our claim, for example, for our null hypothesis, and we need to test that claim with a sample. So what we can do is we can measure people's happiness throughout the day, and let's assume that we get values of 34, 58, 64, 78, which is increasing, but notice that it still increases as you move throughout the evening. So if we were to sketch these distributions out in terms of happiness, what you have here is you have the phi 0 distribution here, right? So that's our phi, our claimed value of the distribution. And then we have our distribution, for example, in orange, right? So obviously both of them do increase up to some point, let's say around, I don't know, 3 p.m. But after that point, you start to see a significant difference between these two distributions, i.e. the theoretical and empirical, also sometimes referred to as the expected and observed distribution values. Now, if you've learned the chi-square test for independence, this might sound very familiar to you, because this first row is in some sense the expected values of our distribution, and the second row is just our observed values for our distribution, where n obviously is equal to 1, 2, 3, 4, 5, 6, and 7, right? So we have 7 sample values, and ideally, if we do have evidence that the distribution of happiness follows this distribution phi 0, then these values of f should be the same as the values above, i.e. their difference should be equal to 0. So let's formally state what our null hypothesis is that we seek to test, and we're going to frame it just like we did for the chi-square test for independence. So this is going to be S comes from a distribution, and that distribution's name is phi subscript 0. And the null hypothesis, the alternative is going to be that S does not come from that distribution. So we can say if phi is the actual distribution, then we can rephrase this in the following manner. So the distribution is equal to some claimed value of the distribution, and the alternative is that the distribution is actually not equal to that claimed distribution value, right? And f is a point estimate for one of these distributions. You should be able to take a guess at which one. For distribution phi, right? So that is our distribution that we're assuming. So this is our parameter, this is our point estimate or statistic, and that is the claim. So those are our three main characters that we typically have in a hypothesis test. Okay, so that is our null and alternative hypothesis. So let's sort of spell out exactly how we will reject and how we will fail to reject. So if we have ideal evidence that phi equals phi 0, then what we will have is that our sample distribution values will be equal to the claim value of the distribution for all x in our sampled domain. So what we can do is we can say that if that is the case, then that means fx minus phi 0x will be equal to 0 for all of those values. And keep in mind, fx is just our observed value, and phi 0 is our expected value. So that means that our observed minus expected value will be equal to 0 for j is equal to 1, 2, all the way down to m. Now, obviously we cannot build a test statistic with n different values, so we do need to combine them. And the way you can combine them in order to get a test statistic that is associated to a chi-squared is going to be this practically the same exact thing like we did for the chi-square test for independence. So our chi-square goodness of fit test, which I'm just going to abbreviate by CG-STAT, so chi-squared goodness of fit test, is going to be equal to the sum from j is equal to 1 to n of, and we're just going to be doing the observed minus the expected squared, all divided by the expected. So that is our chi-square goodness of fit test statistic, and one can show that this is going to be associated to a chi-squared n minus 1 distribution, where n minus 1 is your degrees of freedom, right? And the only way that this distribution is held is if we are not estimating any parameters of our distribution with phi 0. That is, we're not using our sample in order to estimate parameters for which these expected values are derived from. right? So I just gave you those expected values just directly, but you could use the sample mean and sample variance of your sample in order to construct your expected values, right? And then your degrees of freedom would be different, but we're not going to be talking about that here. Right, so we're going to be having evidence that the distribution follows that hypothetical distribution phi 0 if each of those distances are equal to 0. So that means when we look at our chi-square distribution, which has that skewed right shape, our rejection region is going to be in the right-hand tail. Because if it's close to 0, then we have evidence to believe that the distribution is exactly that hypothetical one, i.e. we failed to reject the null hypothesis. And since that's always non-negative, that means this test statistic is going to be always positive, and the farther away from 0, the more evidence we have in terms of rejection. That's what makes this a right-tailed test. Right? So this is going to be a chi-squared, for our example, n-1 distribution. So it's going to be a chi-squared 6 distribution. So if you have some particular value of alpha, you could generate a particular critical value for that. So if we look at our example and you look at that data and calculate our chi-square goodness of fit test statistic, you can find that that test statistic is approximately equal to 11.06. And keep in mind that this is going to be a right-tailed value. So obviously it's not equal to 0, but is it substantially larger than 0? Well, we can always calculate a p-value associated to this, right? So if we look at our chi-squared 6 distribution and plot our 11.06 in this particular picture, this area right here, that's going to be our p-value associated to that particular test statistic. So how do we calculate test statistic in this world? Well, that's actually quite easy. So the p-value is just going to be equal to the integral from our chi-square goodness of fit test statistic to positive infinity of our chi-squared n-1 distribution with respect to that variable. And for this particular value, you're going to find that that's approximately equal to 0.0864. Right, and you can calculate this integral in a variety of ways. For example, that would be p chi-squared in R or some other language, right? So that is our particular p value, right? And let's assume that we have an alpha to compare it to. So let's suppose that our alpha is equal to 0.07, so 7% alpha. So since our p-value is not less than our alpha value, that means we failed to reject the null hypothesis that our distribution follows that particular distribution. That means we have evidence to believe that our happiness value does actually follow that increasing and then decreasing pattern that was hypothesized. But obviously, since our sample size is relatively small, you shouldn't trust it as much, but notice that these two values are relatively close. So if we slightly change our data a little bit, you possibly would have the opposite conclusion, but that's the typical downsides of inference with smaller samples, but this is the chi-square test for independence. Let's introduce another test that can be used for testing the equality or claim value of the median for a sample. So the last non-parametric test that I want to introduce today is actually quite simple, and it's called the Wilcoxon sign test for medians. Now, the Wilcoxon family of hypothesis test actually has quite a few ones. For example, the Wilcoxon sign test for medians, the difference in medians. You could also do it for multiple samples, and also the Mann-Whitney U test is related to the Wilcoxon sign test as well. So they do sort of form a family, but we'll talk about the other Wilcoxon test a little bit later. So the hypothesis that the Wilcoxon sign test for medians says is the following. So let's assume that somebody claims that the population median is equal to some particular number, and let's assume that we want to test against that with a two-sided alternative that m is not equal to m0. So just in case you didn't catch that, this m is the population median, and this is the claim value of that population median. So somebody claims that the median of a population for blood pressure is like 122 millimeters of mercury or something like that. So if you don't remember the median, at least from the continuous perspective, for example, if you consider a exponential distribution, the median value of a distribution is a point such that 50% of the data is to the left of that point and 50% of the data is to the right of that point. So the median, in some sense, is just a fancy way of saying the 50th percentile. So 50% of the data should be less than this median, and 50% of this data should be bigger than this median. And obviously, if you have a point, let's, for example, choose another point on this distribution, for example, here. And let's assume that this area is just 10%, forcing that area to be 90%. Obviously, 10% is far from 50%, just as much as 90% is far from 50%. So if we sort of want to test the value of a percentile, median in particular, pretty much what we're testing is there a significant difference from one of these percentages to 50%? And obviously this is equivalent to using the other one, but we can use either one. But most of the time, the lesser one is the one of interest because it's smaller number in terms of quantity and counting. So let's actually work through an example on how we actually would calculate any test statistics associated to this particular sample. So let's assume that somebody claims that the median age for some population is equal to 47, and let's assume that we want to test that with a two-sided alternative, that the median is not equal to 47. Right? So that is our null and alternative hypothesis. So obviously the first thing that we need to do is calculate or construct a sample from that population. And also the first thing that you want to do is rank this sample from least to greatest. So this is a requirement in order to do the Wilcoxon sign test and several other tests in a proficient way. So let's assume that our sample values from least to greatest are 8, 10, all the way down to 41, 48, 52, all the way down to 176. Now, I'm not listing all of these values. What I'm more interested in is where does 47 fall into place in this particular domain, and obviously here is our claim value M0, which is equal to 47. Let's assume that in this particular sample we have 17 values to the left and 24 values on the right. If that is the case, then we should have some sample size, in particular n, would be equal to 17 plus 24, which is equal to 41. So we know that 50% of 41 is approximately equal to 20, so we should have ideal evidence in the case where we have 20 to the left and 20 to the right. Now 17 and 24 could be arguably close to 20, but we need to do a hypothesis test so that we have an unbiased conclusion of our results, right? So in the ideal case, we would have like 21 on the left and 20 on the right. That would probably be a good outcome if we want to not reject the null hypothesis. And if we want to reject the null hypothesis, then we would have 41 on the left and 0 on the right, or something extreme like that. So let's look at a couple things, because notice that we don't really care about what these values are, we just care about how many there are to the left and how many there are to the right. So a couple notes that you should know, that is, if x is less than the claimed value of the median, then the claimed value of the median minus that value is going to be a positive number, which I'm going to represent with a plus sign. And if x is greater than the claimed value of the median, then the claimed value of the median minus that value is going to be negative, which I'm going to represent with a negative sign. So if I look at my S set again, but I'm not going to look at the ranked values, I'm just going to look at the signed values of that set, then what I'm going to have is just a bunch of pluses, so plus plus all the way down to plus, and then minus minus all the way down to minus. And our claimed value of the median was there, where we have again 17 values on the left and 24 on the right. And since we have a binary set, in some sense we can classify all of these pluses as successes and all of these minuses as failures. And then we can practically set up a binomial distribution setup as long as these observations were independent from one another. So that's a nice requirement for this. So S requires observations to be independent, but again, that's a requirement on the sample, not the population. Therefore, this is still a non-parametric test, at least so far in terms of our development of it, right? So if we sort of continue in this narrative, what can we see? So S signed should consist of 50% plus and also 50% negative. But keep in mind, if the pluses are substantially low, then the minuses will be substantially high. So they're going to be extreme, just opposite spectrums simultaneously, right? And that should be the case if M0 is to be ideally accepted. Or in terms of the more appropriate terms, not rejected. Because not rejected and acceptance are not necessarily equivalent to each other, right? So not rejected, I guess, is the safer word, right? As the median of the population of interest, right? So that's what we pretty much have in the ideal circumstance. So what we have here now is just a hypothesis test on the proportion of pluses and the proportion of minuses in our particular sample. So we can do a proportion test, which we already know is non-parametric. So the proportion of successes in our sample will just be equal to 17 over 41. And we can, of course, calculate the standard error associated to p hat, at least using a walled approach, to be equal to the square root p hat s, 1 minus p hat s, all divided by our sample size, which for our example is approximately 0.077. Right? Now, again, you could use the p hat for failures. Your standard error wouldn't change in that case. You will get equivalent results, though, even though our p hat s and p hat f are complements of one another. In our particular case, p hat f would be equal to 29 over 41. Right? So as long as you're using one, that's particularly okay. So we have our p hat s, we have our standard error. Now we can just calculate our z-test statistic, and we can use a z-test statistic as long as we mandate our sample size is substantially large, so we can approximate binomial with normal, i.e. employ the de Moivre-Laplace theorem. And that's going to be equal to p hat s minus the claim value of p hat s, which is just going to be 50%, because that's what we're comparing to, divided by the standard error of that p hat in the walled sense. And we have that that's going to be approximately equal to negative 1.1045. So that is our test statistic. And since we're assuming that our n is large enough for us to employ this for a standard normal distribution, we can find that our p-value is approximately equal to 0.2671, which is usually larger than most alphas that people choose. Usually alphas are ranging from, say, 0.1% all the way up to 15% usually at most, but of course you can choose an alpha bigger than 26% if you really want to. Right, so let's assume that our alpha is equal to 0.05, then we're going to be failing to reject the null hypothesis that p hat s is equal to 50%, but that's not the original null hypothesis that we were working with, because actually what we're doing is we're failing to reject the null hypothesis that the median of our population was equal to 47. So that's actually our conclusion. And that is the Wilcoxon sign test, which is another example of a non-parametric test. There are, of course, several other non-parametric tests which we will explore later, but for now, I think that that's enough. So I hope you enjoyed this video, and I'll see you in the next one. Take care.